Hello and a very warm welcome to all of you who are attending this webinar of complex numbers. As you can see on the screen, friends, I have tried to give it a different name. I have tried to call it uncomplicating complex numbers. There's naturally a reason to that. And let me be very honest, before beginning, before even telling my introduction, uh, the general purpose, or rather, so to say, the general thought process when it comes to the chapter of complex numbers is not very open in nature. What I mean to say is, I have seen quite a few students. बहुत बच्चों को मैंने ऐसा देखा है. There is an element of doubt when they even start the chapter of complex numbers, when they are not even halfway through the chapter of complex numbers. And that is why I feel it's very important the way you understand the concept, the way you understand the theory behind it. And that is the whole purpose of this webinar, to begin with, at least. Right, we are trying to uncomplicate the nature of complex numbers, the mentality that gets built up, right? And that is what we are going to use and translate into solving problems, gradually building up to difficult problems. So this is the whole purpose to begin with, of this particular webinar, which will translate further into the modular course of the complex numbers chapter that we are going to have in this JEE syllabus. Everyone, welcome to this Vedantu portal. This is my first year in Vedantu, but trust me, the kind of environment we have here, the kind of thought process we have here, the vision we have here is incredible. The whole purpose is, I feel, to reach out to as many students as possible. And I can realize that right now with so many of you attending this webinar, and I can sense that feeling that I can reach out to so many people who I wasn't able to reach out a few years back. Right. So my name is Ganesh Pawar. To begin on that note, if that matters to you, I am BTech and MTech from IIT Bombay, right? What matters to me is I am going to help you, even if I help you, reduce the stress of complex numbers even by 1%. That is what matters to me. That is when I'll feel that mission accomplished, right? So my name is Ganesh Pawar, as I said, and we'll be dealing with complex numbers to begin with. I know there are various kinds of people, lots of students right now. So again, with different thought processes, with different levels in terms of the understanding of complex numbers. I'm pretty sure ऐसे कुछ बच्चे होंगे. There might be a few students who have no idea of complex numbers. There will naturally be a few people who I was speaking about, who feel that complex numbers is a difficult chapter. Conceptually समझ में नहीं आता. Why complex numbers? What complex numbers? All these questions hover around, and that is what creates a hurdle. That is what creates a roadblock into understanding complex numbers. So that is what I want to make sure कि conceptually ये idea clear हो जाए. Conceptually it becomes so smooth that when it comes to problems, you can look at it from a very different perspective. So changing perspectives is the idea, and naturally we'll be gradually dealing with much more difficult problems through different approaches. So that is why uncomplicating complex numbers, right? So yes, friends, let's begin today's webinar. I'm really happy and really proud to be doing this, and let's have some fun. Why not? So before beginning rather, the idea of complex numbers, as I said, right, before beginning the idea of complex numbers, as I mentioned, that one of the question comes, why complex numbers, right? Why? What is the use of complex numbers? I have heard this quite a few times, right? Maths में ये चीज हम क्यों पढ़ते हैं? Why do we study a particular kind of this topic? We have heard that trigonometry के applications हैं, arithmetic के applications हैं, right? There are quite a few things which do have applications, but why complex numbers, right? And that is why I have this, I thought of doing this thing for you guys. Like, why not just Google and search what are the real life applications or practical life applications of complex numbers. And here we are. I came on a page on Quora and got onto this question: what are some real life applications of complex numbers in engineering and practical life? Right? Before even going to what complex numbers are, थोड़ा देख तो लेते हैं कि क्या है, मतलब क्यों complex numbers है. Naturally, when you go through this particular page, you should keep this in mind that you will not be able to understand each and every method of the application. What you need to take from this particular slide, take from this particular tab on the browser, is that these all are the possible applications of complex numbers. How are they applied? That is something which is level 10. Because since we don't know level 1 and level 2 of complex numbers, we won't be able to understand exactly how level 10 occurs. But what we need to understand is there is level 10, and that's what we are going to do here. So as you can see right on the screen, basic application, before even going into too much detail, there are high words like signal processing, digital communication, image processing, compression. Then there is something called as discrete Fourier transforms. That is the method of application I was talking about. So basically kya ho raha hai, that there is an image which is encoded into a Fourier transform. Now have a look at this. Does this look like this at all? No. So it's basically encoding any image into something which can be decoded again to get the original image. So that is the purpose of one of the purposes, rather one of the I won't say infinite, but one of the many purposes, applications of complex numbers, right? And the application method is discrete Fourier transforms, which we don't know, level 10 as I said, but ye hota hai, and this is quite practical and real. So right, it's definitely a real and practical life. As we move forward, you can see that there is a piano, right, like a synthesizer, so to say, and it does have electrical signals. And if you read onto it, you will see there's a term called as convolution, transform, multiply, and stuff. Again, DFTs, discrete Fourier transforms. So again, all of these things have complex numbers as a very major component in them, right? And this is indeed real life. And as we move forward, there are so many other stuffs, right? Quantum computations, and as you move forward, there are phasor diagrams, and then you can see circuit diagrams where we have resistors, capacitors, inductors. All of them have a very major component of complex numbers involved into them, right? Now at this stage, you will feel that wow, complex numbers does indeed have so many tremendous amounts of applications. So why not? It should be fun. So let's go back to level 1 and have a quick look, right? Have a rather not a quick look, rather let's understand level 1 first, basic, and then level 2. Gradually समझने की कोशिश करेंगे, and then if life allows you, and rather if you are more interested into it, you can definitely dive deep, right? Without any fear that complex numbers are scary. Remove that element out of you. Now as we go forward, you can see that there is an application in aerodynamics as well, in the wing of an aeroplane. Wow, that is something that imagining would have been difficult. कि complex numbers यहाँ पे भी use होता है. That clearly shows complex numbers has immense application. It just does not stop. All right. So all you have to do is come back and enjoy complex numbers, and that is what exactly we are trying to do. That's what exactly we'll be trying to do. Fearlessly try and understand the level 1 of complex numbers, the basics of complex numbers. Now we have understood that why complex numbers, there is so much amount of usage. Now we'll understand how complex numbers, how they are generated, what they are, and then we'll go on to the problems that will help us tremendously in solving difficult JEE problems as well, right? So on that note, let me move on to a story, right? Let me move on to a story to understand complex numbers a bit more further. I'm pretty sure many of you already know what complex numbers are. Z equal to A plus IB, the polar form, the Euler form, right? And I'm pretty sure many of you must have solved a countless number of difficult complex numbers problems as well. Yeah. So as I can see in the chat box, there is a lot of response, and everyone is having fun with the application, and they are having their opinion about this particular slide. As you can see, it's a pretty interesting story that I tried to build it up. I'm not sure if it is if you can relate to it, but it's pretty cool. Let's have a look at it. All right. So let's say here is you, right? I'm very bad at drawing, so please forgive me about that. Here is you, a simple common man or a woman, right? Wanting to go on the rooftop of this building for Batman's rooftop party, right? Definitely not complex numbers right now, right? But let's stay with the story. Let's stay with the story and have some fun. Let's see, right? We're just trying to see how the basic idea that I would suggest right now is please be open. Please be in terms of thought process, please be open. Try and explore नई चीजें सोचने की कोशिश करो. Don't try to restrict. Try keeping on having an open mindset. Try understanding new stuff. Again, as I said, you already know what complex numbers are, but this is going to be a different direction in understanding complex numbers. Right now, Batman calls you. All right, Batman is on the rooftop already, and anyways, like even if it is anywhere else, he can like zoop 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 and come on the rooftop directly, right? Because he's Batman. Yeah, you are not. I'm not. All right. So the idea is, you want to go to the Batman's rooftop party, and Batman tells you that, dude, you have to, considering I can see you where you are at this particular position, giving your coordinates or whatever. You have to. Just follow these particular instructions and reach this rooftop party. It's pretty amazing, right? He says you'll have to walk in this particular direction for 10 units, let's say 10 meters. Yeah, then you have to perpendicularly change the direction and walk for 5 meters, let's say, and then you have to climb the stairs and come up for 20 meters. Right? So basically what has happened is, try and visualize the scenario. You are at this position. Batman says that 10 meters in the x-axis direction, 5 meters in the y-axis direction, and 20 meters in the z-axis direction. This is all you have to do to reach my rooftop party and have a lot of fun. Right? Everyone clear till this part of the story? This is all has to be done to reach that rooftop party. So one thing that is noticeable here, that all the 3 steps that you have to do, 10 meters in the x-axis, 5 meters in the y-axis, and 20 meters on the z-axis, so to say, all these are lengths, right? Numbers, but in terms of length, 10 meters, 5 meters, 20 meters, correct? Right? At the end of the phone call, Batman tells you that you have to reach here within 2 seconds. If you don't reach here within 2 seconds, right? Let's try to make it simple. You have to reach here within 2 minutes. Not complicating this. So the whole purpose is uncomplicating. So you have to reach here within 2 minutes. If you don't reach here within 2 minutes, you will be denied entry, because that's the rule of the party. Like the party entry stops in like 2 minutes, and if you don't reach here, you won't be allowed. So all your efforts are in vain, right? Yeah, vain. Okay, if at all people know about Dark Knight, Batman, yeah. Okay. Anyways, so 10 meters, 5 meters, and 20 meters. But the the crack is 2 minutes. Now, if you think about it, that 2 is also a number, like 10, 5, and 20 are. But the idea is that 2 is of a different unit. More importantly, it's of a different dimension. Can you understand that? Yeah, think about it. Think of it from that perspective. 2 minutes, right? So what is happening in this conversation, rather what is happening in this problem is there is a different dimension that's been introduced, right? And the different dimension here in this particular scenario is time, right? Now, what this example tries to convey, what this example, friends, tries to convey is that, in a particular problem, in a particular scenario, once you add a different dimension, yeah, the story opens up, the problem expands, so to say. And that is what exactly complex numbers do, right? When you say z is equal to a plus ib, you have that extra dimension which gives rise to complex numbers. When you say z is equal to a plus ib, right, this plus holds for nothing. If you look at it, you cannot add these two numbers. Why? Because even if a and b are numbers, they are of different dimensions. This belongs to the real dimension. Yeah, a belongs to the real dimension and b belongs to the imaginary dimension, right? So think of it in this way. trying to just simplify complex numbers. Complex numbers basically क्या है अभी अगर मान लो आपने शुरू ही यहाँ से किया था, if you would have started only from the point of z is equal to a plus ib, you must have at one point, may have at least thought of this, that why like how a plus ib, like what is the purpose of this, right? The idea is you can write a complex number in this fashion: 2 plus 3i, where 2 and 3 both are numbers, but both these numbers represent two different dimensions altogether. This represents the real dimension and this represents an imaginary dimension, right? Like in this case here 10, 5 and 20, right? 10, 5 and 20, 10, 5 and 20 represented the length dimension, and 2 minutes represented the time dimension. So in the same problem we had two different dimensions, right? And hence it became complex. And in this scenario we have two numbers, but that I helped us create an imaginary dimension. Just by putting that I, it helped us create an imaginary dimension, right? I hope from before a bit more improvement in terms of understanding what complex numbers are, why they are represented in this fashion. The need for this was created in the 16th century when mathematicians, being mathematicians, wanted to solve the equation of x square plus 1 equal to 0, and then they realized that x square is always positive or 0, right? And that positive or 0 number added with 1 can never give you 0, right? X square cannot be equal to -1 ever in terms of real numbers, right? And that is where the need for an imaginary component came into place, and that gradually translated into tremendous amounts of applications, right? और इसी से शुरू हुआ था, x became root of -1, which we call I, and that gives rise to an imaginary dimension, an imaginary component. So we have one complex number, one input, so to say, which has two components, two dimensions to it: the real component and the imaginary component. Yes, friends. So yes, this is the beginning. This is how it all started. Yeah. So now let's move forward to understand the same thing on the Argand plane, right? Everyone knows about the XY axis. I'm pretty sure, again, like quite a few of you are saying as well, that this aspect was interesting understanding from this way. It indeed is. Although again, the major component, the major part is to understand how to put this on the Argand plane, put all of this understanding of complex numbers on the Argand plane, and understand the various formats of complex numbers and translate it into problems, solving problems. So that is what we are gradually heading towards. But before that, Argand plane, these complex numbers, each and every complex number can be plotted on the Argand plane. As you can see, I've already plotted a few complex numbers to have a generic view of it. The Cartesian plane had the x and y axis. Keep this in mind. This is not the Cartesian plane. This looks like the x axis. This looks like the y axis, but this is the real axis. And this, my friends, is the imaginary axis, right? So whenever you have a complex number, yeah, you can place that complex number onto this Argand plane. Now keep in mind, when we talked about real numbers, we used to represent the real numbers on a number line. Yeah, we used to represent the real numbers on the number line. Beech mein 0 tha, right at the middle there's 0. All of this is positive numbers, all of this is negative numbers. Now this is just the representation of real numbers. Now when it comes to representation of complex numbers, because complex numbers have two dimensions, because complex numbers have two components, you cannot represent them on a line. You have to represent them on a plane with two components represented by two axes, the real axis and the imaginary axis. So this is not the Cartesian plane. What used to happen in the Cartesian plane, here is a small look over here. I hope everyone can see this. Yeah, a small look over here. The Cartesian plane, x-axis, y-axis. X was the input and y was the output. Right, this is the one of the quadratic equations: x square minus 5x plus 6. X is the input and y is the output. Here, my friends, this is the real component and this is the imaginary component. There is no place for output as of now here. This is just the Argand plane. Yes, I know there can be complex functions as well, but you cannot represent them. I'm getting those kind of doubts as well. Hold on to this, friends. First, try and understand that here you can represent complex numbers as inputs, right? जैसे यहाँ पे आप number line पे करते थे, like in one dimension, you used to represent them on a number line. Here, for representing complex numbers, you need two axes. One is the real axis, one is the imaginary axis. So we treat the y-axis as the imaginary axis and plot the complex numbers like this, right? So these are just the inputs. So if I say I have a complex number z equal to a plus ib, a, you have to find it on the real axis, positive if positive here, negative here, and b will be represented on the imaginary axis. You find that coordinate and you get that point. That point represents that complex number, only that input. Unlike here, when you plug x as 1, right, when you plug x as 1, you'll get 2, so 1 comma 2. So that's the output of the function y equal to x square minus 5x plus 6. The input is just 1. Yeah, the input is here, the output is here, and hence you have this point on this function. Function वाली बात हम लोग complex numbers में अभी तक गए नहीं है. This is just the plain representation of complex numbers. So coming back to this, representing complex numbers on the Argand plane, let's say this is a plus ib. As you can see, a is 2 and b is 1. So this complex numbers 2 plus 1i can be represented by a point p with the coordinates 2 comma 1. Right, there will be ample amount of properties which are related to that, which we'll gradually explore, but I hope everyone has understood how the complex numbers can be depicted. Likewise, we have 2 minus I, 2 plus minus 1i. 2 is the real component, minus 1 is the imaginary component. 4i, which can be written as 0 plus 4i, so 0 being the real component and 4 being the imaginary component. 4, which is basically 4 plus 0i, 4 being the real component, 0 being the imaginary component. Now this very point tells you one thing, that all real numbers are complex numbers indeed, but all complex numbers are not, right? So this particular point clearly shows that this is a real number, but as well as a complex number, and hence you can say that, you know, you can just represent it by this fashion, that this smaller circle is a set of all real numbers and the capital circle is all complex numbers, right? So this number 4 will come here right inside. Yeah, because it can be written as 4 plus 0i and simultaneously be plotted on the Argand plane as on the real plane, real number line rather, right? But these numbers cannot be plotted on the real number line, on the real axis, right? Minus 3 plus 2i, minus 3 on the negative real axis, plus 2 on the imaginary axis, right? So this is how we you know, represent complex numbers. Again, as I said, quite a few of you must be pretty thorough with this, pretty clear with this. Try and understand the you know, the geometrical representation of this, which is what is more important, getting a sense, because as I said right at the start of the class, the idea today is to understand complex numbers from a more graphical or a geometrical perspective, so that we can create a connection with it. And that's the whole motive right from the start, to understand complex numbers, to make it simpler. That is what the whole target is. And definitely we'll go to problems, difficult problems, to make it more fun and interesting, because at the end it's all about applications, right? Coming to applications, I have a sweet little problem over here. Right now, this problem can be solved in multiple ways, as I believe like almost all problems can be, right? As it says, there is a complex number 1 plus root 3i upon 2 the whole raised to n, right? And it says that a be a set of complex numbers where n is a positive integer. How many distinct elements are there in set A, right? So how many different complex numbers can be possible? Yes. Good that I can see a few people attempting and you know, asking questions about this. Hold on, friends, hold on to that. We are not going to solve this question now. We are going to build up a bit of a theory so that we can see the simplest way of solving this. Trust me, after the modular course, I really feel if you were scared of complex numbers, or if you feel that, you know, I'm not very confident about complex numbers, although I know quite a bit of theory, I've solved quite a few problems, but you know, I'm not able to get that connection very clear. I cannot feel complex numbers. Trust me, at the end of the modular course, I genuinely feel that you can even solve this problem mentally, as I have seen quite a few students doing that. And that is what you know, the fun, the interesting part of complex numbers is. You can feel them, you can relate them. Once you get the concept clear consciously, then you know, it's like muscle memory. Your brain automatically starts sensing the location of the complex number. Where does this complex number lie? How does this move? How does that n affect it? That's what exactly we are going to do, right? So we'll come back to this. There's another interesting problem, right? Both of them integer type question, and both of them have the capability to go into a JEE advanced level. This says how many complex numbers are conjugate of their own cube, right? I'm again pretty sure quite a few of you definitely know what a conjugate is. Conjugate of a complex number a plus ib is nothing but a minus ib. So you keep the real part same and make the imaginary component negative of the original, right? So that is what it is. Yeah, the question is how many complex numbers are conjugate, how to come back to this position, how to come back to this particular question, right? By different methods. We'll go to that. But before that, let's try and understand the polar and Euler form. Let's try and understand the polar and Euler form, right? Here we have, yes. So now, there are two major components, rather three. The third one is the conjugate. Two major components of a complex number z equal to a plus ib. That is the modulus of a complex number and the argument of a complex number. I'm not going to go too much into depth of finding them. They're pretty trivial, so to say. If you know complex numbers beforehand, we are definitely going to go too much in absolute depth in our modular course about modulus and argument. But just for the basic sake, let's say if you have a complex number z equal to a plus ib, right? If you have a complex number z equal to a plus ib, then modulus of the complex number is root of a square plus b square, right? The modulus of the complex number is root of a square plus b square, correct? This is the modulus. And the definition of modulus, one second. The definition of modulus is nothing but, I'll just write modulus and argument over here to get a brief definition. Yeah, modulus is distance from origin, yeah, of the complex number, rather the point representing the complex number, right? So basically, if this complex number is represented z equal to a plus ib, complex number is represented by the point p, then OP is what the modulus is, and hence the formula comes out to be root of a square plus b square, right? And secondly, argument is nothing but angle that OP makes with the positive x-axis. That is what argument is, yeah. And then there is the concept of principal argument as well, which basically says that a principal argument is the only argument which lies between minus pi to pi, and which naturally gives rise to the concept of argument, which says that there are infinite arguments of a single complex number only depending upon the angle. So let's say if we have 30 degrees as an angle, it is absolutely same as 390 degrees, and then it's absolutely same as 390 plus 360, which is 750 degrees. We can go in the reverse direction clockwise as well, and all these angles will be the argument of a complex numbers, and only that angle which lies between minus pi and plus pi, which is basically minus 180 and 180, will give you the principal argument, right? So this is about modulus and argument, right? And using these two components, using these two concepts of a complex number, we can easily create the idea of the polar and Euler form, and that is what exactly we are going to look at, friends, here. Yeah. So just to get a better idea of it, let's take a complex number z equal to a plus ib in the first quadrant. As you can see here, the modulus is written as r, which is nothing but root of a square plus b square, right? A is this component on the x-axis, B is this component on the y-axis, naturally the real and the imaginary components respectively. R is root of a square plus b square. Yes friends, right? जिसको हम modulus कहेंगे. Theta जो है, theta is the argument, right? And theta can be found out by trigonometry, basic trigonometry. Tan theta is b upon a in this case, and there are various techniques of finding argument. As I said, we'll be doing those elaborately in our modular course, right? Now, when you look at this particular triangle, you can sense that cos theta is adjacent upon hypotenuse. So cos theta is a by r, and r cos theta is a. Similarly, sine theta is opposite upon hypotenuse, so r sine theta is b. That helps you in converting the original complex number z equal to a plus ib, which is written in its Cartesian form. We call this form the Cartesian form, where the complex number z, friends, is written as the real part plus I times the imaginary part, right, of the complex number, which can be now converted using these two. Using these two that we have just figured out, हम a को r cos theta लिख सकते हैं और b को r sin theta लिख सकते हैं, correct? And once we write that, we get our polar form. This is what we call as the polar form of a complex number, right? We take the r common and we can write this as r bracket cos theta plus I sin theta. This is the polar form, friends. And how this is useful is because we can write the original complex number, which was in the real plus I times imaginary format, into another format, and both of them are naturally the same, right? Into another format which is written in using two components again. One is the modulus and one is the argument, right? One is the modulus and one is the argument. So r cos theta plus I sin theta, now that can be written again as r e raised to I theta. Right now, this is an interesting part. Quite a few of my students have asked me, कि sir हम ये कैसे लिख सकते हैं? Like, what is the explanation behind this? How can I write r cos theta plus I sin theta as r e raised to I theta? And every time I say the same thing, and I'll repeat the same thing again here, that अभी के लिए assume that cos theta plus I sin theta is e raised to I theta straight away, right? R को हमने वैसे ही लिखा है, r cos theta plus I sin theta we have written as e raised to I theta. First, trust the concept over here, trust me over here, and all these three things are same. Z equal to a plus ib, r cos theta plus I sin theta, and r e raised to I theta, where a is the real part of z, b is the imaginary part of z, r is the modulus of z, and theta is the argument of the z, right, of the complex number z. E is nothing but the Euler constant 2.71828. It's an irrational number like pi. Now coming to the point कि why ऐसा हम क्यों लिख सकते हैं, ठीक है? After understanding कि ऐसा है, उस बात पे आते हैं कि क्यों हम ऐसा लिख सकते हैं. There are at least two proofs of proving this. Cos theta plus I sin theta is equal to e raised to I theta. There are two mechanisms of proving this. One is using series, and the idea is both these proofs, right? I'll share that link to you as well as and when we go into the modular course. The thing is, at this stage, if you are in your 11th grade, it will be slightly difficult for you to understand that, because both those proofs require concepts that are related to your 12th standard syllabus. Basically, integral calculus ke concepts, infinite series ke concepts involved hai usme. But using those concepts, you can very easily prove this, right? But now is not the time to go into that. Once you do those concepts, we can come back here and make sure that this is right. For now, we have to understand and appreciate the idea that this is one of the most useful formats of writing a complex number. The reason behind that, friends, is that this Euler form helps us deal with indices, right? E raised to I theta jo hai, helps us deal with indices, and this is what is going to help us solve those two problems that we had before, right? I hope you remember them. Right, but if you have understood the polar form and Euler form nicely, here are a few complex numbers. Yeah, we have the Argand plane as well. Try and convert all these four complex numbers into their respective polar and Euler forms. Right, even I'll do the same thing. I'll give you about 4 minutes because there are four complex numbers. Type in your answers, at whatever pace it's possible. Right, and I'll solve at the same time, and then at the end you can have a look at your answers as well. Right, come on friends, let's apply. I hope everyone has understood. If you have a complex number z equal to a plus ib, आपको उसका modulus ढूंढना है, right? आपको उसका argument ढूंढना है, and then you can write its polar form as r cos theta plus I sin theta, where r is the modulus and theta is the argument, correct? And then you can write this as the Euler form as well. So yes, friends, come on, begin. Let's see. Wow, I am already getting answers. That's awesome. That's great. That's cool. Nice. That's right. Mm-hmm. Yes, Z3 does not have a real component, so yes, it will lie on the imaginary axis. That's correct. See, the best thing, friends, is to find, obviously finding the modulus is pretty easy. I can, clearly see that. It's about finding the argument, right? Something that we have not discussed in great detail, but finding the argument, the best thought process is सबसे पहले उस complex number का quadrant locate कर लो. Locate the complex number first, the quadrant of the complex number. That will help you tremendously in finding out how exactly the argument is placed. And by use the basic definition, the argument is nothing but the angle from the positive x-axis. Correct? So use that. Mhm. That's nice. Good response. Yeah, Z2 is tricky. I hope, like I'm getting mixed answers. That's good. That's good though. Gradually you will understand कि किस तरीके से the idea that I was talking about, how to figure out the argument. That's the key here actually. So Z2 is interesting by that regard. The second complex number. That's correct. Nice. Yes. Nice. Nice. That's really nice. All right, friends. Let's have a quick look. Let's have a quick look at all the answers. So whoever has got the answers, please verify, check their answers, and I'll ask me doubts. Whoever feels that they have a doubt, right? I'll just quickly go through Z2 maybe. Yeah, Z2. The thing is, first you need to, since quite a few of you are asking about Z2. Z2 को एक बार ध्यान से देखते हैं. Right now, finding out arguments of any complex number has a formula as well. Something that we will again see in the modular course. But then, I feel the better way is to locate the position. एक बार position देख लो, and as I said some time back, कि there will be a point in the course of complex numbers where you start sensing कि वो complex number कहाँ पे है और उसको किस तरीके से move करना है, चीजें कैसे affect कर रही हैं, how the things are affecting the complex numbers, right? So just consider this minus root 3, so negative real component, minus 1i, so negative imaginary component. So this complex number lies somewhere here. Notice that the real component is root 3 and the imaginary component is 1 in terms of length. So root 3 is bigger than 1, and this is how roughly it would lie. Now when I connect, naturally, finding modulus is very easy. Modulus of Z2, which is represented by this, is nothing but root of minus root 3 the whole square plus minus 1 the whole square. Finding that is pretty easy. And you can say that this is, 3 plus 1, root 4 is 2. Yeah. So finding the modulus is pretty easy. That's a cakewalk. The idea is finding the argument, right? Now, keep this in mind that this is the argument. Or you can say that this is the argument. Yeah, both of them, angle made by the positive x-axis for OP, right? Now, for finding these angles, this or this, both of them would be correct. What you want to find is this angle, right? And for finding that angle, you drop a perpendicular. This length, the imaginary component length, we know is 1. This length, the real component length, is root 3. Now, if this is theta, friends, if this is theta, can I say tan theta is 1 upon root 3? Yeah, can I say tan theta is 1 upon root 3, and can I hence say theta is equal to 30 degrees or pi by 6, right? Now if this angle is pi by 6, can I say that the argument of z2, yeah, can I say the argument of z2 is nothing but pi plus pi by 6, yeah, which is 7 pi by 6. So this is one possible argument. At the same time, can I say that this argument through the clockwise direction, agar hum clockwise jayenge, so can I say it's minus pi plus pi by 6, yeah, minus pi plus pi by 6, and that comes out to be as minus 5 pi by 6, which is what I have written here, right? In place of this, you can very well go ahead and write 7 pi by 6, right? Even that would be considered, right? This is just the principal argument. The reason behind that is, principal argument lies between minus pi and pi, right? Or you can write this as this minus pi se pi में principal argument lie करता है, including pi and excluding minus pi, right? So now friends, if we are able to understand complex numbers in the Cartesian, polar and the Euler form, now naturally all of these can be written in the polar form. Just आपको ये r जो है वैसे ही लिखना है, bracket करके cos of ये angle लिखना है, cos of this angle plus I times sin of the same angle, you'll get the corresponding polar form. Correct. So now friends, if you are clear with converting a complex number into its polar and Euler, particularly Euler, which is what I was more interested in, why not let's go back? Why not let's go back and try to answer this question? Yeah. Everyone take a minute, ponder over it, and naturally now कि ये complex number को Euler form में convert करने से चीजें बहुत easy हो जाएंगी. I had already got a couple of right answers for this, which is pretty amazing. So I want every one of you remaining people जिनको लगता है कि complex numbers difficult है, polar form, Euler form नहीं समझ में आता, not understanding polar and Euler form, or for that matter how to deal with difficult questions of complex numbers, attempt this. As I said already, take that inside complex number 1 plus root 3 I by 2 and try and convert it to its Euler form and make life simpler, right? Make life simpler by doing that. Let's go ahead and do that, friends. Come on, everyone. I'm drawing a Argand plane again, so that for the after once you convert it into the Euler form. Yes, that's correct. Yes. Quite a few of you are already getting the right Euler form for this, which is pretty amazing. Now try and raise that to n and see how does that exactly affect. Yeah, think about this, right? This complex number 1 plus root 3 I by 2, if you find the modulus, you will see that the modulus is 1, right? And the the argument, right? The argument of this complex number is pi by 3. So 60 degrees you can say, or you can say pi by 3. I'll take 60 degrees here. Generally, I prefer, I rather ask everyone to write it in the radian format, because it helps a lot as we move forward into understanding more difficult concepts. But here we can write 60 degrees because we want distinct elements. So let's have a look. What does this n exactly do? Yeah, what does this n exactly do? N is a positive integer, so the first number that I can take as n is 1. And when I have 1, can I say that this number, right, 1 raised to n will always be 1, so that is not going to get affected at all. Yeah, n times 60 degrees, or you can say n pi by 3, however you want to put it. Yeah, this is always going to be 1. Now, that is where the indices wala aspect has helped us a lot, right? When n is 1, you get a complex number. Naturally now, all these complex numbers with as n changes, all of these complex numbers are going to lie on a circle. And that circle will have a modulus 1, because you can see when you write this in its corresponding Euler form, agar aap Euler form dekho, so it's r e raised to I theta, right? And r is the modulus, and here the modulus is 1. That means each and every of these complex numbers जो A के part में है, all those complex numbers which are part of the set A will have a modulus 1. Modulus 1 means distance from the origin is 1. So all of these complex numbers will lie at a distance from the origin of 1. That means they'll lie on this circle of unit radius, right? I hope everyone is clear with that aspect. right? Now the first complex number when n is 1 lies here. Yeah, when n is 1, it lies here, right? Basically e raised to I 60 degrees, a complex number with modulus 1 and argument 60 degrees. Now when n is 2, it will lie somewhere here, 120 degrees. Yeah, I hope everyone can see that. Yeah, this is 60 degrees. This is 120 degrees, right? Now when n is 3, the complex number will lie here because it's 3 into 60 degrees, which is 180 degrees, right? When n is 4, it will become 240 degrees. When n is 5, it will become 300 degrees. And when n is 6, it will become 360 degrees. Yeah. What about when n is 7? When n is 7, it will become 420 degrees. But friends, 420 degrees is nothing but 360 plus 60. That means 420 is nothing but 60 again, right? And when you put n as 8, you get the same complex number again. So basically what is happening is you are actually getting 6 different complex numbers, and that is what your answer is. That is what exactly they are asking. How many distinct elements are in set A? 6. End of story. Integer type question. Done. Good JEE advanced question, right? And if you think about it, once you get a hang of it, ये पूरा diagram आपको दिखने लगेगा. You'll start sensing this diagram in your brain if you get comfortable thoroughly with the polar and Euler form. Specifically the Euler form. I'm just saying polar form only because the Euler form is generated using the polar form. Correct? Right? So I hope you have got this and it was fun. Right? Now on that note, let us move to this next question. This is also an interesting question. Yeah. Yes. See, the thing is, in this question, I'm getting a doubt about you know, n being integers, how to deal with the angles. See, the thing is, I can totally understand. Gradually, you will get used to how the Euler form goes. Here, you need to understand कि indices को लेके use हुआ है. This n can get multiplied with 60, and if you consider r e raised to I theta, this is the modulus. Yeah, which is always 1 in this case. I hope you have understood that, because nothing is written here, that means it's 1, and this is the argument, right? So here the argument is 60 degrees n or n pi by 3, right? जैसे n change होगा वो argument change होगा. Modulus हमेशा 1 होगा. Modulus will always be 1. The argument will keep on changing. 60 degrees, 120 degrees, 180 degrees, 240, 300, 360. It will still keep on increasing as you go forward. But the idea is, as you go forward, you are getting repeated roots. You are getting rather repeated elements, and you want distinct elements, right? And the distinct elements are only these 6, because after that they are going to get repeated. What I mean is 420 is same as 60 when it comes to the argument of a complex number, right? Cool. Yeah, that's great. So let's come to this one now. How many complex numbers are conjugate of their own cube, right? Without complicating the problem, let's first write down what it says. How many complex numbers are conjugate of their own cube? Is this what the complex number says? Think about it. Is this exactly what? Yes. Yes, you have to use the polar form. That's correct. Yeah. How many complex numbers are conjugate of their own cube? This is what it has been saying. उसका cube का conjugate कितने complex numbers हैं, right? Yeah. Yes, that's correct. Oh, brilliant. Yeah, 2 people have already given the right answer. Yes, all you have to do is write it in the polar form, Euler form rather. That makes life much simpler. And as we go forward, you will also realize that using polar form, using Euler form is like a real blessing. It's a real boon, so to say. Yeah, 1 second, I cannot write that. Yeah, first of all, I need to write r e raised to I theta, which is z, the whole cube, the conjugate of that. This is what my right hand side is. The left hand side is pretty easy to understand, right? I'll just continue with the right hand side. This will make it r cube e raised to I 3 theta, right? Now the conjugate of this is the idea. Now the thing is, whenever you have a particular complex number, friends, let's go back to the Argand plane, right? Whenever you have a complex number, let's say this, and when you ask for its conjugate, the conjugate will have the same modulus. The length from origin is still going to be the same, but the angle, if the original angle was theta, the argument, the conjugate's argument is minus theta. I hope everyone can see that. अगर 30 degrees है एक original complex number का argument, तो उसके conjugate का argument जो है minus theta होगा. The argument of the conjugate is going to be minus theta, and that's exactly what we are going to use in this problem, right? So r cube, the modulus remains the same, so that is unharmed, and this becomes e raised to I minus 3 theta, right? So we have r e raised to I theta, right? Now comparing, obviously, e raised to I theta has to be compared with e raised to I minus 3 theta, and the magnitude has to be compared with the magnitude, right? So I can say that r is equal to r cube. This gives you two things. Yeah, this gives you two things after solving. One is r is equal to 0, right? And another is r square equal to 1. Therefore, r is equal to plus 1. Now, don't ask me why r is not equal to minus 1. Yeah, so naturally, modulus cannot be negative, right? So we have to discard the minus 1 number, right? We have to discard the minus 1 number. R is equal to only plus 1, right? And r is equal to 0 is also possible. Now, when r is equal to 0, if the distance from the origin is 0, there is only one complex number which is possible, which is the origin itself, right? So z equal to 0 is one possible complex number, right? Now, when r is equal to 1, distance from origin is 1, right? Distance from origin is 1. So complex numbers satisfying this will again lie on that unit circle that we considered in the previous problem. Yeah, unit circle of radius 1. Now the thing is, for this we need to understand that theta is going to be minus 3 theta, right? If not exactly, you can say that 2n pi minus 3 theta, correct? And you will notice, friends, that this is possible. This is possible on the imaginary planes, right? So basically, यहाँ का एक number possible है. You can just put numbers and check. You will get this. 4 theta is equal to 2n pi, and gradually you will see that theta is equal to n pi by 2. Right? Now, when you say n pi by 2, n is an integer, right? You can take n as 1. When you take n as 1, friends, you will get pi by 2. When you take n as 2, you will get pi. Yeah. When you take n as 3, you get 3 pi by 2. And when you take n as 4, you get 4 pi by 2, which is 2 pi. When you take n as 5, you get 5 pi by 2, which is again the same number. When you take 6, you get 6 pi by 2, which is 3 pi. Again, you get the same number. So that is why playing with angles is very important. Now you can clearly see you have 4 complex numbers, right? With modulus 1 and argument 0, pi by 2, pi, and 3 pi by 2. So basically this complex number is 1, this complex number is I, this complex number is minus 1, and this complex number is minus I. These 4 complex numbers, all having the modulus as 1 and their corresponding arguments, will satisfy this basic condition. Also, there is z equal to 0, and hence the correct answer is 5, right? So there are 5 complex numbers who are the conjugate of their own cube. And you can very easily plug all these 4 numbers now in this equation and see them getting satisfied, right? So I hope, understanding these 2 problems from the perspective of Euler form has helped you a lot in understanding that complex numbers के problem सिर्फ algebraically solve नहीं करने हैं, but you always need to have a feeling towards it. You always need to have a graphical perspective, an Argand plane perspective of it. It helps you see through the problem more, and that naturally helps you solve the problem at a much faster pace than it generally can be, right? So I hope that has helped, and using that logic, let's go forward to do a few more problems using the geometrical funda. That I think that will be really great. Let's move forward. I have one more nice interesting problem over here. It's relatively simple though. It's relatively simple, but let's try and do it with playing with the Argand plane rather than doing it geometrical, rather than doing it algebraically and using the properties, which is something we'll definitely do in the course, modular course. But right now, let's try and connect with complex numbers using the Argand plane and playing around with the angles and having the graphical edge of it. So here in this question, it has been said that Z1 and Z2 be two non-zero complex numbers such that their modulus is same, right? And it has been said that argument of Z1 plus argument of Z2 is pi, right? Argument of Z1 times the argument of Z2 is pi. So, naturally here you can think of it as a property argument of Z1 into Z2 is pi. So, you can apply that thought process as well. But what I am thinking is, why not वो सब properties में जाने से अच्छा, why not just think of it in terms of Argand plane, and why not let's just take examples and just see where the complex number is lying and whether it satisfies the given condition or not. Let's try and do it that way, right? Since the modulus is same, it's very evident that distance from origin is same. Yeah, and if distance from origin is same, they lie on the same circle. I hope everyone is getting this idea that distance from origin is same, they lie on the same circle. Let's say the modulus of both of them is 5, right? Modulus of both of them is 5. Each and every point lying on this circle will be at the same distance from the origin, will be at the same, having the same radius, 5, right? And hence Z1 and Z2 will be any 2 points lying on this circle, can be any 2 points, right? Now it has been said that argument of Z1 plus argument of Z2 is pi. Now let's try and play around it a bit. Let's say, and the question naturally asks you to represent Z1 in terms of Z2, right? The question asks you to write Z1 in terms of Z2. Now, if I say that Z1 is 30 degrees, argument of Z1 is 30 degrees, let's just say that. So मान लो Z1 यहाँ पे lie कर रहा है, right? Now for argument of Z1 plus argument of Z2 to be equal to 180 degrees, to be equal to pi, don't you think argument of Z2 should be 150 degrees? If Z1, right? If Z1 is equal to 30 degrees, don't you think so Z2 should be 150 degrees? Just taking an example. Yeah, just taking an example. Don't you think Z2 should lie here? Think about it. Yeah, this is 30 degrees. Yeah, and this one is 150 degrees, because the net sum of these two angles has to be 180, right? So this is one possible case. If Z1 is lying at 60 degrees, Z2 has to lie at 120 degrees. So basically, can you see that Z1 and Z2 are basically mirror images with respect to the imaginary axis, to be very precise? Right? मान लो अगर Z1 यहाँ पे है, the argument being minus 30 degrees, for them to add to pi, for them to add to 180 degrees, Z2 has to lie here and have the argument as 210 degrees, so that the 210 and the minus 30 gets balanced and gives you pi, gives you 180 degrees. So basically Z1 and Z2 are mirror images with respect to the imaginary axis, correct? Once that fact is established, right? Once that fact is established, we can say that let's say Z1 is represented by the point A comma B. Basically Z1 is the complex number A plus IB. Then since it's the mirror image, we can clearly say that Z2 का जो x coordinate होगा, the real coordinate, mirror images with respect to the imaginary axis, y-axis or the imaginary axis. We know that we cannot call it the y-axis because it's not the y-axis, it's not the Cartesian plane, it's the Argand plane. So the y-coordinate is going to remain the same quite naturally, and the x-coordinate, the real coordinate, is going to be minus of a. Yeah, so we can clearly say hence that Z2 is equal to minus a plus IB. Now the question is, we already know Z1 and Z2, how to represent Z1 in terms of Z2, right? All you have to do is understand what Z2 bar is, right? If Z2 is this, you can clearly say that Z2 bar is nothing but minus a minus ib, right? And which can be written as minus of a plus ib, right? And now we can take the minus on the other side. So minus z2 bar is equal to a plus ib, which is nothing but z1. So z1 hence can now be written as minus z2 bar, which is option D. And this process can be thought of mentally. You can very clearly see that as well, right? The conjugate of z2 is here, and this is right the negative of this. So z2 bar and the conjugate of this. So even this process can be thought of graphically, which is the amazing part of thinking geometric, thinking complex numbers problems from a graphical perspective, right? So this is cool. I think we can definitely have a look at another problem before we stop our webinar. But before that, let me just express the modular course in front of you, because that's pretty important. As you can see, here we have the link of the registration of the modular course for complex numbers. We are going to have 5 classes, maybe 6 if required, for completing the entire complex number syllabus, complex numbers 1 and 2, if at all you are aware of that. It will include all the algebraic concepts and the geometrical concepts. And as you saw in today's session, we'll try to make sure to build up a connection between you to make life simpler when it comes to complex numbers. We've already seen that complex numbers has immense amount of application, right, in the real world, in the practical world, in the research world. But the thing is, to get to that stage, first, the fearlessness attitude is what is important, and that is what we'll be targeting throughout the course, to make life simpler, to uncomplicate complex numbers. So friends, here's the link. Have fun and to enjoy this course, register. And as you can see, there's a lightning offer that you have, right? The course price is generally $2,000, which is 1999, and the thing is, the lightning price right now, only for the 4 hours, the next 4 hours, as it has been told to me, is $1,000, which is 999 only, right? And so do register, and I'm sure that we can have a lot of fun over it. And there were a few more interesting aspects actually that I wanted to do today, but I'm thinking let's keep it for store. Let's keep it for store. There was an interesting problem which has 2 different approaches, and both these approaches give 2 different answers. So let's see, if I get an opportunity, we'll have another webinar if possible, and after that we'll go on to the modular course and discuss all minute aspects of how to be how to look at a complex number problem from different perspectives, and which perspective helps when: the geometrical perspective, the graphical perspective, all the algebraic. The whole idea is to solve problems as fast as possible. So कितने जल्दी से जल्दी हम problem solve कर सकते हैं, वो करने की कोशिश करेंगे हम ये पूरे कोर्स में, and that will be our whole idea. On that note, here's one last problem for the day before we end today's webinar. It's going to be fun. Everyone, please try, and as you can see, it's more graphical in nature. So try and plot this problem onto the on your Argand plane, and quickly get back to me. Let's see. So it says that we have a square P1, P2, P3, P4. These are 4 points drawn on the Argand plane, where these points are representations of these 4 complex numbers: Z1, Z2, Z3, and Z4. Z1 is a complex number 1. It's a real number as well, but it's a complex number as well, right? Z3 is a complex number 3. And what we have to find is the product of these 4 complex numbers. So I'll give you a couple of minutes to go ahead with it. Yeah, let's see who gets this first. It's an interesting problem. It will be fun. Parallelly, I'll also solve it for you. Definitely, I would want to draw the Argand plane to make life simpler, as we have seen in today's session. Here is my first complex number Z1. Here is my second complex number Z3. I mean, the third complex number Z1 and Z3 are here. Right? Now, for this to be a square, don't you think so? The only possibility is this. I mean, the Z2 and Z4 can be reversed, but apart from that, this is the only possibility. और कोई तरीका ही नहीं है स्क्वायर बिल्ड करने का. correct? All of them naturally are 90 degrees, right? This is 1 comma 0, the point coordinates 3 comma 0. Now we know this is 2 comma something and this is 2 comma something. The reason behind that is pretty natural due to the symmetric nature. This is the diagonal and this is the diagonal, and they'll intersect at the midpoint of these two, and that will be 2 comma 0. So this is 2 comma something, 2 comma something. We don't know what that something is. Let's call this B. If that is B, won't this be minus B? Yeah, again due to symmetry, right? So 2 plus IB is this complex number Z2. 2 minus IB is this complex number Z4. Now how to find that value of B? Now comes the property of square, that diagonals are equal, right? Diagonals are equal. So can I say P1, P3, the length P1, P3 is equal to the length P2, P4? Yes, I can say that, right? Right, now what is P1, P3? Can I say that the length of this diagonal is 2 units? Yeah, and the length of this diagonal, friends, if you carefully look, is 2B. Yeah, because this is B and this is B. The length of this diagonal is 2B, the length of this diagonal is 2. Therefore, sensing that B is 1, we have all the 4 complex numbers now. Yeah, we do have all the 4 complex numbers. Think about it. Z1 is 1, Z2 is 2 plus I, Z3 is 3, and Z4 is 2 minus I. Now all you have to do is multiply. Keep the 3 aside, 1 does not have any significance. 2 plus I into 2 minus I will give you 2 square plus 1 square. Yeah, simplifying that, a plus ib, a minus ib gives you a square plus b square. So that's 5. 5 into 3, 15 will be the answer for this question, right? So yes, friends, hope you had fun. I definitely had a lot of fun, and let's just hope we have a very interesting modular course. So don't spend any time, because I really feel you need to grab onto this opportunity and make sure that we have a lot to learn in complex numbers, like we did in the quite a few problems that we did today. We tried to understand stuff from the Argand plane, putting things on the plate, having a deep look at it and connecting the dots. That is what we are going to do. Although apart from that, there's going to be a lot of algebraic stuff related to complex numbers as well. So yeah, best of luck. I'm really excited to see you all in hopefully the next webinar and the next the modular course, which is lined up after that as well. Right, so here's one problem which I wanted to share with you guys. You can have a look at it and copy it down in your notebooks, solve it, and definitely again it's a tricky question. It's an easy question though, but it's tricky in a nature, in the sense of how it has been put. So yeah, go ahead, have fun with it, and we'll reveal the answer soon, right, when we meet next. Bye bye, take care, have fun, enjoy, friends.